recap what we did yesterday. Here we go. So I guess just a little reminder. So yesterday in my lecture, we talked about that gamma rays are absorbed by the EBL. Oh, sorry. That this absorption feature can be used to actually constrain the EBL as well. So we've seen how gamma rays have been used, for example, to constrain the star formation rate density. And then we switched gears a little bit and went on to axions and how they solve the so-called strong CP problem, which is essentially a tuning problem over 10 orders of magnitude and stems from the non-observation of the electric dipole moment of the neutron, I should add here, which is, however, predicted in QCD but not observed. And then we briefly touched upon that these axions and axionic particles are predicted in the standard model of particle physics, or in extensions, of course, of the standard model of particle physics. Okay, so what we're going to talk about today, so we essentially pick up where we left off. So I first want to tell you how axions and axionic particles can act as cold dark matter. And then we transition more to the theory of photon axionic particle mixing. So we're going to look at some equations here, but don't be scared. We will take a detailed look also in the hands-on session. So I hope you get a feeling of how these oscillations occur in the end. And since this mixing of photon and axionic particles happens in astrophysical magnetic fields, we need to look at the relevant astrophysical magnetic fields. And Walter nicely touched upon some of the fields that are also relevant for us. And then in the end, we will look at axion searches using gamma ray observations of AGN. Okay, but first let's play the same game as yesterday. So please open your laptop or go on your phone and go to menti.com. And today we're going to use this code 67842583. So let me just see if people are joining. So again, here is the code 67842583. And yeah, maybe send a little emoji here so that I know that you are here. Excellent, very good. Great. Good, question marks. Okay, very good. People are joining, so I think we can get started with the actual lecture, and we come back to, I think I have 2 questions for you during the lecture, and then in the end, you can also actually pose questions here, which I forgot yesterday. Okay. All right, so first off, if we want axions and axionic particles to be the dark matter, we need a so-called non-thermal production mechanism. So what does that mean? So first off, often when we talk about axions and ALPS, we talk about light axions and ALPS. So with light, I mean lighter than 1 electron volt. And why do we need this? Because we want them to be stable against the decay. And axions and axionic particles, they can decay into 2 photons. And this is their decay time. So it's given. Oh, there's a square missing here, sorry. So it's essentially given by the inverse of the coupling to photons squared times the mass to the 3rd power. And in numbers, this is this. So the decay time will be something like 10 to the 25 seconds multiplied with the coupling, the power of -2, mass, power of -3. So this means that if you increase the mass now, or you increase the coupling, that this lifetime goes rapidly down. And then you get a problem, because if you just use these values here, which we'll look again later, then you're perfectly safe. Your lifetime is 10 to the 8 gigayears, which is much, much longer than the age of the universe, which we believe is something like 30.8 gigayears, which you would like, right? Because you want your dark matter particle to be stable. So this is necessary for axions being dark matter. But if you now increase the mass or you increase the coupling, that this lifetime's down rapidly. So if you were talking about the same masses as WIMPs, for example, so your mass would be 1 giga electron volt, so that would be 10 to the 9 electron volts. So this would be 10 to the 9 to the power of 3. So that would be that give you a factor of 10 to the -27, and then you run into trouble. Okay, but now if axions are now, in the very early universe, when everything is sort of a hot plasma, and these particles can be produced just by interacting with standard model particles and all the particles that are in this hot soup. They would be produced with quite a large velocity. So they would not be cold dark matter, and then they would not really contribute to structure formation. They would rather be warm or hot dark matter. So, but if we want the cold dark matter, right, that we need for structure formation that we have observed, for example, in the fluctuations of the cosmic microwave background, we need some other production mechanism. They need to be produced what we call non-thermally. Okay, so let's look how axions and ALPs actually evolve in an expanding universe. And this is governed by the following equation. So if you have just a scalar field in the early universe, then its evolution in time is given by this equation. So your axion field is A. So A dot dot is just a second derivative with respect to time. Then you have this term here, where H is the Hubble parameter. And here you have the mass of the axion. And because of you can have interactions with all other particles to which the axion potentially coupled, this can actually get radiative corrections and thus might also depend on time. Okay, so it's governed by this equation. So we have the Hubble parameter that relates to this scale factor through this logarithmic derivative. So the Hubble parameter is just R dot over R. H naught is today's Hubble constant. And R is what goes into the Friedman equations of an expanding universe. Okay, so this is the so-called scale factor for those of you who have had this in a cosmology class. Okay, but what does this equation remind you of? Think maybe, mechanics 101. So think, maybe. So unfortunately, I can't really hear you if you scream this at me now. But maybe some of you realize that this looks very much like a damped harmonic oscillator, okay? And it actually is. So we can use all the tricks that we've learned how to solve this differential equation. We can also apply those here, and we can actually get some insights about the physics. Okay, so let's look at this. So in the very early universe, this term here, this will be much larger than this term, okay? Because the Hubble parameter will be much larger in the early universe, and then it will decrease in time. So in the early universe, you have an overdamped harmonic oscillator. So nothing is oscillating here. So the field will be frozen at some initial value, AI, that is, for example, given by this misalignment mechanism. Okay, and then the universe starts expanding, it starts to cool, and what happens is that this parameter goes down, and at some point, these two terms will be equal, and then the field will start oscillating. Okay, and let's say this happens at some time that we call T oscillating, or equivalently at some temperature, right? The universe is very hot in the beginning, then it cools, and at some point it has cooled enough. This is the temperature where it has cooled enough so that the field starts oscillating. Okay, and this is now the picture that you saw yesterday, right? So in the very early universe, our additional symmetry is not broken yet, so we're sitting here. And then at some point, the temperature will have gone down to a new energy scale where the symmetry is broken, so the field goes down in this Mexican head potential, and we are here. And this is also around the time, or then at some point, these two terms will be equal, so we will start an oscillation. So this is now the field value as a function of time. So this will start oscillating. We also will, at some point, get to the temperature where we have a QCD phase transition. And at this point, we will have these oscillations around the minimum, okay? And then these oscillations, they decay a little bit in amplitude, okay? So this is kind of the picture that we're having here. Okay, so just some more details. So we can solve this equation through the typical WKB like ansatz, so that our field has some amplitude that could vary in time, and then also a phase that could vary in time, where the assumption is that the amplitude A is slowly varying in comparison to the phase. Okay, if you plug in that ansatz, then you find that the field strength as a function of time is just given by this. So you have essentially integral over the mass, how the mass changes over time from the time when we start the oscillations until today. And then you have this the combination of the scale factor and mass, where m ost is now the mass when the oscillation starts, and this is the scale factor when the oscillation starts. And here you have your initial field value. Okay. And so in this case, what we find actually is that the axion behaves like a perfect cosmological fluid that has some energy density and some pressure. And you can calculate these values. So these are the typical equations for a scalar field for energy density and the pressure. And what you find is that the energy density is essentially given by the combination of the mass ratios, the scale factor ratios, mass today, and also this initial field value. And this is what we call this initial field value, is essentially the initial misalignment of the field. So how far up we start in this potential well with the oscillations. And this is why this mechanism of producing these axion oscillations is also called the initial misalignment mechanism. Misalignment. This is the initial field misalignment. And if this was zero, right, if we would start at the potential minimum, then we wouldn't have any energy density here, and then axions couldn't be any dark matter. So we need some initial value. Essentially, we need to start oscillating. We need to start the oscillations from a certain height. If you think of a pendulum, for example, and if we don't have that, then okay, there's no energy density. There's no dark matter. And it's actually possible to show with these expressions that the cone moving number density n is just it's just the density of the mass, and it goes as the scale factor to the power of -3. So as the universe expands, this is actually conserved. So this number is a conserved quantity. And also, if you do a time average over the pressure, this is actually equal to 0. And then you can get your equation of state. You essentially just divide pressure over density, and this is 0. And this is exactly what you want for cold dark matter. Okay, so these are exactly the properties of cold dark matter. So what does it mean now? So that means that you have to think of the axion field as a classical field in this picture. And this classical field will have oscillations, slow oscillations. And these oscillations give you some energy density and some pressure. The pressure is 0. The energy density on average is given by this expression. And this has the exact same properties as your wimpy cold dark matter, for example. Reality might be a little bit more complicated. So far we have looked kind of at this picture here. So we have assumed that the symmetry is broken before inflation ends, sorry. So what does that mean? So at some patch, some patch will be, through inflation, will be expanded exponentially to be essentially our horizon, everything that we can observe. And in this patch, the initial field value will be the same. So the initial field value in the very early universe could be different at different spots, but through inflation, we actually only observe one patch where the misalignment is the same everywhere, and then we get exactly the picture that I told you about now. And this is the case if the symmetry breaking, or if the symmetry breaking, this FA, is occurring at very early universe before inflation stops. So as I said, initial misalignment will be the same in the entire observable universe. But it could also be different, that this new symmetry is broken after inflation. And what will then happen is that the universe will have different patches with different initial misalignments. And then you can get something that is called topological defects. So we actually have two regions with different initial misalignments. Then you will get these so-called defects that then could decay into axions. And then most of the axion dark matter is actually given by the decay of these so-called topological defects. Okay, so we have only discussed a simple scenario, but this could actually be much more complicated as a side note. But the takeaway is that if we have this initial misalignment, then axions could be cold dark matter. Okay, so this I was showing already yesterday. This is the axion L parameter space in terms of its mass and in terms of the coupling. And let's just have a little bit more details here. So this yellow band that you see here, maybe I can actually draw this. Let's see. Like this. Oh. Okay, no, it doesn't work. Sorry. Anyway, so now we can. So this band that you see here, this is what people usually refer to as the QCD axion band. So where the axion actually solves the strong CP problem. And these are theories beyond the standard model that give you sort of a simple prediction where this axion should be. But don't take this carved into stone. So the axion could actually, that solves the strong CP problem, could actually also live here. and could actually also live here. So many people are working in the theory departments to see, okay, what parameters are actually possible for the axion to solve the strong CP problem. For axion to be dark matter, this is usually the case. I think it's in the next plot, but it's usually there's something like a line here, and you need to be below this line to have axions as a dark matter. Okay, and then also it needs to be somewhere here, because if you are in this regime here, then if you are somewhere here, then the decay time is too short for axions being dark matter. Okay. So what else do you see on this plot? You see a lot of colored regions, and these are constraints. So people have looked for the axions using astrophysical probes, using laboratory experiments. So far, no one has found any sign of the axion. And what we'll talk about today is essentially the parameter space up here, so very light axions. And we'll understand at the end of this lecture why we need to look at these very light axions and axion-like particles. Or I should say, I say sort of axions and axion-like particles interchangeably, but in these standard scenarios, these are only axion-like particles we're looking at because we're far away from this QCD axion band. Okay. So conclusions for this first part: axions can solve the strong CP problem. Axions and ALPS are cold dark matter candidates, and we need this non-thermal production mechanism through the so-called misalignment mechanism. Okay, and now let's go to photon ALP mixing, how we can actually search for these particles. So the Feynman diagram that we need for this is this one. So the axion could oscillate into a photon in the presence of an external magnetic field. And this is what we'll use exclusively throughout this lecture. So you could also turn this a little bit around, and you could have the decay integer of the two photons that I also briefly touched upon yesterday. But today, it will only be oscillations between axions and photons. So both directions are, of course, possible. Okay, so we start off. Now comes a little bit of a math part, which might be boring to some of you. That's totally fine. But stay with me. I think there is some interesting phenomenology that I would like to discuss here. And at least you've seen that. And after this, you've seen once the idea how to solve these equations. And it's actually not that difficult, I would say. So you can sit at home, sit down and do it yourself. So this is why I think it's nice to show at least once, and then you can stash it away somewhere. Okay, so there's some literature here that you can follow that nicely reviews this. So I don't give a detailed derivation here, just the main steps. So we start typical sort of for particle physics. We start with the Lagrangian density of the photon ALP system. We take current density to be 0 since we assume vacuum, and we take natural units, so h bar equals to c equal to 1. Okay, so first off, we want to describe the photons. So this is sort of the kinetic term for the photons. This is the electromagnetic field tensor. I have it in the backup slides for those of you who don't remember it. And then you have this additional term here, which you might not be familiar with. And this is what people call the Euler-Heisenberg Lagrangian. And it essentially encodes one loop corrections to the photon propagator, right? So you have the photon propagator here, and this could form, for example, an electron-positron loop, interact with external magnetic fields as well. So this is all encoded in this beast here. Then you have the kinetic term of the axion and the mass term of the axion. This is just standard scalar field. And then you have the interaction term. And this is given by the coupling strength, which is some constant, times the electromagnetic field tensor and its dual. This is also given in the backup slides. And if you just multiply these two matrices, you end up with this kind of simple term here. So they have your field strength, axion field, electric field of a photon, and your external magnetic field B. Okay, and this is this Feynman diagram. And then you just add all this together. And then you derive your equations of motions from Nernst's theorem, right? So you just calculate I mean, this is some algebra you have to go through, but you solve these, or you write down these equations where your fields are the photon field and the axion field. Okay. Some details given in the backup slides. Okay, so where do you arrive? You arrive actually at an equation that looks very much like a Schrödinger-like mixing equation, where the propagation direction, let's call it the z-coordinate, so the axions are propagating along the z-axis, takes the function of time in the Schrödinger equation. So it looks like this. So you have here the energy of the axion, You have here the derivative with respect to the z direction. Yeah, Schrödinger equation, that would be direction of time. And then you have a mixing matrix here. And then you have here your different field components. So you have two photon polarization states and the scalar axion field equal to 0. And this mixing matrix is given by this thing here. And these delta terms are sometimes referred to as momentum differences, and they have the dimension length to the power of -1. And what is important here, so when you look at this mixing matrix, you see that this perpendicular polarization, which is given by this here. So assume you have some magnetic field, external magnetic field, polarized into one direction. And then you have one photon polarization state parallel to it and one perpendicular to it. And you see that the perpendicular state, this one here, completely decouples from the axion, right? If you would just multiply this mixing matrix with this vector, you see that the perpendicular component completely decouples from the axion. What is important is that the parallel component, so this polarization component, so propagation comes outside of the blackboard towards you, that this mixes with the axion through these off-diagonal terms here. There could also be terms here in the off-diagonal. This is important, for example, for radio observations that Walter also touched upon. It's called Faraday rotation. We'll briefly touch upon that later. But this is neglected here, sorry, since it's not important for gamma ray energies. Okay, so let's take another look at this mixing matrix. So first off, what is this delta perpendicular term? It's this beast here. So let me just quickly go through what this all means. Then you have this parallel term here, also a sum of more of these delta terms. And the first one is this plasma frequency. So in a medium, the photon will not be massless, but will have sort of a mass that is this plasma frequency, and it's just given by the electron density and some combination of charge and mass. Then you have this QED birefringence term, which will become important later. So if the magnetic field is really strong, you will actually be more likely that you have these additions to the photon propagator by just electron-positron loops forming. And this is decoded through this term here. Now, vacuum birefringence, so you can actually change the polarization by propagating through vacuum with a strong magnetic field. And this is decoded here. And these effects become important at very high magnetic fields. Then you have what is called photon-photon dispersion. So actually, if you're propagating in a background photon field, these photons can actually then again interact with the photon. And this is given by this term here, will not be so important in this discussion. Then you have the Alp kinetic term. This is this last off-diagonal term with just the axion mass. And then in the end is the mixing term. And this is what is important to us. And you see the mixing is then proportional to the coupling and the magnetic field. Okay, oof, lots of algebra. So let's just one more slide on solving these mixing equations. So what you do is you can solve this with what people call a transfer matrix. So the ansatz is that your state Z is just a state at Z equal to 0. And then you have essentially a transfer matrix that brings you from Z equal to 0 to Z. Yeah, and this psi is just given by the vector I was showing you before. And you can find these transfer matrices. And the first step that you do is you diagonalize this mixing matrix and you find the eigenvalues. And then you do the superposition ansatz here. And the eigenvalues are just, the first one is just the decoupled one. And the second one is given by this combination here. And where this term, this is important. This is the this oscillation term, which is again, combination of these delta terms that we had before. And it's essentially the inverse of the oscillation length. Okay, and then you have also a mixing angle between the two, between the photon and the axion state, and this is given by this term here. Okay, so now I've shown you all of this, and the idea is that if you have heard about neutrino oscillations, these ALP oscillations are these photon ALP oscillations are very similar to this. The only thing is that you need extra is this external magnetic field. So the oscillation probability is then very similar to what you find for neutrino oscillations. And here you have this delta oscillating term here. And this is how it looks like. So essentially what you want is that if you want to have a lot or a high conversion probability, you want this delta os times Z, you want this to be small. or conversely, you want a long oscillation length for your axion field. Okay, so let's just have one more look at this term here. You can actually reformulate this a little bit. So if you just pull out, if you plug in, or if you just pull out this term here in front of the brackets, yeah, you just pull this term out, and then you plug in the definitions of these terms that I was giving you a few slides back, you find that you can express this term in this way, okay? And now remember what I told you the slide before, we would like this to be as small as possible to have large oscillation probability, okay? So how do you do this? You want these two terms to go away. So the energy should be much larger than this minimum energy, and it should be much smaller than this maximum energy. And this minimum energy is given by this combination, which you can then plug in all these values. This is what you find. And you have your maximum energy, which is given by this, and this is what you find, okay? Okay, so mixing will be strongest if you are in an energy regime in between this minimum energy, which is given by a combination of the plasma frequency, the mass, coupling, and B field. And if the energy is much smaller than this maximum energy, which is given by a coupling magnetic field, again, magnetic field and dispersion term. Okay. So let's have a look at an example. So enough of equations. So let's assume we have a magnetic field that has a field strength of around a microgauss, is coherent, so essentially constant along 10 kiloparsecs. So this is roughly what you can assume for the Milky Way. We have a coupling given by this value and a mass 10 to minus 8 electron volts. So if you would propagate an axion through this magnetic field, this would be the oscillation probability. Okay, so it would be of the order of a few percent, and it would be constant at maximal between this minimum energy and this maximum energy. And here it's very simple. It's just described by 1/2 times the coupling times the magnetic field times the length over which the magnetic field is constant. Okay, very simple. So what we could look for then is, for example, a boost in the gamma ray flux, because here gamma rays could, instead of interacting with the extragalactic background light, they could just oscillate into axion-like particles, and then very close to Earth, maybe oscillate back. And in this way, you could circumvent this absorption. Or you could look at energies where you have these oscillations in energy, right? And these oscillations in energy, they would just be imprinted on the spectra of for example, AGN blazars. We've just seen that we expect these spectra to be very smooth, right? From all the emission processes that we've discussed so far, leptonic, hadronic, they're all very smooth in energy. They don't have these oscillation features here. So these are the observables that you can actually look for. Okay, so takeaways from this longish discussion. Photon outmixing is maximal for these energies. And we expect spectral features around this minimum and maximum energy. Okay. So, okay, let me think if we go to the quiz now or later. I think we just take one more thing and then I'll let you do some work. Okay. So at which wavelength or frequency or energy should we observe? Okay, so what I'll plot here as a function of energy and magnetic field, I plot now this minimum and maximum energies. Yeah, equations are given down here. Okay, so if you plot, so in this gray region, the energy will be larger than its maximum energy given down here, right? So here we will have no oscillations or very strongly suppressed oscillations, okay? So we can forget about this region altogether. Everything that is below here, here the energy is much smaller than this minimum energy. This is given for some mass, but 10 to the minus 12 electron volts. So again, here it won't make sense to observe, you know, a source that has a magnetic field of a microgauss to observe this as radio frequencies because we won't be able to see any oscillations if we want to search for axions. And this now, as you increase the mass, right, this shifts upwards. Yeah, so if you're interested in axions that have 10 to the minus 9 electron volt mass, then we have to observe sort of in this window here. And if we go to 10 to the minus 6 electron volt, then we have to, there's only sort of a tiny little window left where we can actually expect any oscillations. And if we go to even higher masses, then essentially everything is filled up. Okay. So the QCD axion for this particular value in coupling, so this is all for one coupling. So if you change the coupling, this plot will look differently. But for this coupling value, the QCD axion lives at 5 times 10 to the minus 2 electron volt. So it lives somewhere here, right, along the line here. So there's no chance that for this coupling, we can actually observe photon axion oscillations in astrophysical scenarios. All dark matter in the form of axions. For this coupling, we have it for masses above 10 to the minus 6. So there's actually just a little tiny window left here. Okay, so it will be hard to discover dark matter axions with this couple. Okay, so in this regime, we can actually use X-ray and gamma ray searches from galactic and galaxy cluster fields. Yeah, galaxy clusters will have a magnetic field 10 to the minus 6 Gauss. So we can actually look for, if we look at the energies here, this is gamma ray to X-ray. We can also use gamma ray searches from AGN fields. AGN fields can have, in jets, can have magnetic fields of around a Gauss. So here you can use nicely gamma ray energies. There are also other sources. So for example, linear polarization from magnetic white dwarfs. These have very strong magnetic fields, 10 to the 9 Gauss or so. So here we can use optical observations to look for features. And then actually at these highest magnetic fields that we have in neutron stars, we could, for example, look for dark matter converting into photons and the magnetospheres of these neutron stars. And we can look for those in the radio regime. Okay, so now let's go to Menti after all this discussion. Let's go here and go to our first question. So let's think a little bit about which of the following statements is not correct, okay? So if we increase the axion-like particle mass, this will shift the minimum energy to higher energies. Is this correct? Yes or no? Increasing the alt mass increases the conversion probability. Is this true? Yes or no? Decreasing the magnetic field also decreases the oscillation probability. Okay, is this maybe true? Or decreasing the magnetic field increases the maximum energy. Okay, so take a second. Think about what is not correct. Maybe I'll show you. Let me show you the slide again with the formulas. Right. Maybe this one, yeah. So these are the formulas for the minimum energy. Depends on the mass squared, inversely on G and B. This, okay, let's forget about this term, right? And it becomes simpler. Then actually 1 power of B is canceled, and then it's just G over B for the maximum energy. Yeah. Okay, we have head-to-head race. No one is brave. Say this is wrong. Decreasing magnetic field increases Emax. This you don't like. Many of you don't like. Oh, now you see the answer, right? So you just follow what everyone else is saying. Okay, let me solve this. So it's actually this one. Increasing the alt mass increases conversion probability. So why is this? Yeah, you just have to look at the formulas essentially. So so you can see it clearly in this plot, right? So when we decrease the magnetic field, what happens is that the maximum energy goes up. Yeah, this is given by this line. Yeah, and this you can see from this formula here. Let me zoom in. Right, so if we forget about this term, so it's just G over B. Right, so if you increase B, you decrease Emax. Okay, so this statement is actually correct. Yeah, very good. Another vote here. So decreasing B also decreases oscillation probability. This is correct, right? Because this plateau here, where this occurs, this is just G times B times L. So if you increase B, you also increase the oscillation probability. So increasing the alt mass increases the conversion probability. But the conversion probability here is independent of the out mass. It doesn't matter. So the height or the amount of oscillations, of the oscillation probability, the value does not depend on the mass, but it depends. The mass only says where is this minimum energy. This is important. Okay. So a lot of things to think about. Okay. So let's continue. Okay, so some caveats. So far, we have only talked about homogeneous magnetic fields. Astrophysical magnetic fields, however, are usually much more complicated. They're turbulent. They change along the light of sight. They change the strength. And the initial photo beam is often unpolarized or only partially polarized. Okay, so this means that if you have both this perpendicular polarization and the parallel polarization, both are make up 50% of the polarization, then at most 50% of photons can oscillate into axial path. Okay, and if you include all of this, this will make the solution to the mixing equations much more difficult. Okay, so let's talk about the magnetic fields that we have that are interesting. So let's look at this plot, and it's actually the Hiller's plot that you've seen, I think, yesterday. Ulysses showed this. So do you know any magnetic fields? Okay, so let's go back to Menti and go to the next slide and see if you know any magnetic fields. So we've done this. Oh, okay, next slide. Here we go. So do you know any astrophysical magnetic fields? In which environments? What is their strength? Any idea? So just go wild. Type whatever you want. Any astrophysical magnetic field. Okay. Not your LHC magnet. Good. One answer. Anyone else? Here's for guess 2 answers. Very good. One more, and then we can actually look at them. I see you were much more firm with charge and parity violations than with magnetic fields. So maybe there are a lot of particle physicists in the audience. Okay, let's see. What have people said so far? At least one you should know. Oh, very good. Now more answers come in. Very good. So let's take a look. No, that's a fair answer. That's definitely a very fair answer. AGN is right. I just said it. It's 0.1 Gauss. Interstellar magnetic fields, micro Gauss. Yeah, in our Milky Way. Very good. Yep, magnetars. Galaxy, micro Gauss, extragalactic, nano Gauss, or weaker. Very good. Neutron stars, solar jets, intergalactic. Very good. Neutron stars, galactic center, 2 Gauss. I'm actually not sure about that. Nano Gauss and intergalactic. Yeah, these are just limits though. Extragalactic. Yeah, we'll cover those. Galactic magnetic fields and micro Gauss. Yeah, very good. Okay, starburst galaxies, also micro Gauss, neutron stars. Actually more. Neutron stars have more like can have up to 10 to 12 Gauss or even higher. I've never met any of them. Oh yeah, you have at least met one. This is the magnetic field on Earth. So okay, very good. Excellent answers. Excellent answers. So let's see. So here we go. So this magnetic field you know, and you've experienced it. At least if you once had your compass out, you've actually seen it at work. Okay, and this is of course how more or less a Gauss is defined. So the Earth's magnetic field is a Gauss. Okay, and here you see the lines that Ulysses was showing if you want to accelerate cosmic rays, right? But you have neutron stars, which are very compact but have very high magnetic fields. You have your AGN, you have AGN lobes that's also Walter touched on. You have galaxy clusters. You have intergalactic magnetic fields. So there are a lot of regions here that might be potentially interesting. Okay, so if we now take the example of a blazar, right? We're observing a blazar in gamma rays. So what magnetic fields are relevant here? So we have magnetic field inside the source, the order of a Gauss, so maybe, factor 10 higher or lower. We have the host galaxy. So the AGN lives inside a galaxy. Typically these are elliptical galaxies that have micro Gauss field strength and lengths of the order of 100 parsecs. You have the termination lobes of your blazars, very similar magnetic fields as in the galaxy. The AGN could live inside a galaxy cluster, where you have again magnetic field of the order of micro Gauss, which are coherent. of the order of kiloparsecs. They change randomly throughout the cluster. Intergalactic medium, some of you already mentioned that. Here we only have upper limits, so we know that the magnetic field has to be weaker than a nanogauss. And we actually don't know a lot about the coherence scale. Could be megaparsec, could be higher, could be much lower. And then you also have the Milky Way, again, very similar magnetic fields, coherent on the microgauss or strength of a microgauss length scale of a kiloparsec. Okay, so let's quickly go through some of the observational evidence that we have for these magnetic fields. Since I'm running a little bit out of time, but that's fine. We can cover all the things I don't get to today. We will cover this a little bit in the hands-on session and also tomorrow. Okay, so jet magnetic fields. You've seen images like this in Walter's presentation. So the presence is inferred from, we see synchrotron emission from jets. For this, we need magnetic fields. We see polarized emission, again, clear sign of magnetic fields. And we also see the rotation measures, which means that the rotation angle actually rotates. And we also see the core shift, which Walter also briefly mentioned here. So this means that we see the most of the radio emission, or where we see the most radio emission is actually depending on the distance to the central supermassive black hole as a function of frequency. So the high frequencies we only see further out. The low frequencies we only see further out, and the high frequencies we see further in. And from this, you can then the magnetic field actually. This is due to essentially synchrotron self-absorption. The structure of the magnetic fields, we believe it has some helical shape, which you can see here. And which is inferred from these images that Walter was showing. The poloidal component, we think that this dominates at the base, and then the toroidal component actually dominates at larger scales. And this toroidal component is actually what can lead to photon axion oscillations. And it's probably coherent in pretty large scales, but it also has some turbulent component on top. And these findings are also supported by general relativistic magnetohydrodynamic simulations of these jets. So here's a simulation of these jets, and you see here you have this nice helical structure. Okay, so these are the jet magnetic fields. So going further, magnetic field in galaxy clusters. What observational evidence do we have here? Also synchrotron emission, also rotation measures. Rotation measure is essentially given by the change of the angle of the polarization. And this scales as the wavelength squared times this rotation measure. This rotation measure is the line of sight integral over the density of electrons and the magnetic field component that is parallel to the line of sight. So this is not the magnetic field component that is important for photon axion mixing, but if we think that these magnetic fields are turbulent, if there's a parallel component, there should probably also be a perpendicular component. So these are this is a map of a galaxy inside the Coma cluster, and you see rotation measures here. And from this, you can infer field strength up to tens of microgauss that extend out to a few megaparsecs. So here is essentially a measurement, and this was true, or I think this comes from a simulation. Yes, this comes from a simulation from the Coma cluster, and you see the magnetic field is stronger in the center of the cluster. And as you move out in the cluster, the magnetic field goes down, following essentially the electron distribution. Yeah, so this is usually what we see in galaxy clusters. The magnetic field strength follows the electron density. Then you have the intergalactic magnetic field. So for the intergalactic magnetic field, the idea is that it acts as a seed field for all the magnetic fields that we see in galaxy clusters and in galaxies. So this is a cosmological simulation, the illustrious TNG simulation. This is a box of a few hundred megaparsecs, and here's the magnetic field. And so the extragalactic magnetic field should be at its seed strength, should still be there in cosmic voids where we don't have a lot of matter. This is extremely hard to measure directly, so these are only simulations. So what we get from rotation measures are only upper limits of the order of nanogauss. And from indirect measurements from gamma ray observations, which we won't cover here, you get lower limits. We have limits that say, okay, the magnetic field should be larger than a femtogauss or so. And then coming to the magnetic field of the Milky Way, again, what's the observational evidence? You might have an idea. It's polarized synchrotron emission. So synchrotron emission, always helpful, that we see with Planck and WMAP satellites. And we have, again, rotation measures from background sources that then, for example, send radio waves that go, that propagate through our Milky Way. So here's a rotation measure map of our Milky Way. And then we have models. So one of the latest observations is already 10 years old now, but I don't think there's a much newer version of this. They have different components. So there's the magnetic field in the disk, where you see nicely the spiral arms. Here's the Earth. Then you have a halo. So this extends above and below the disk. And you also have, in these models, you have also this X component. So Earth is here, and you have, in addition to the halo, you have this X component because these field lines have this X kind of shape. And if you take this model and then you calculate the photon, and the B field is actually here on a large scale, but also has a turbulent component. But if you take, for example, this model here, and then you calculate what is the photon oscillation probability for something coming from outside our galaxy going in all the way to us, then this is what you find. Yeah. So for this value of the coupling, if you have, these are actually gamma ray bursts here. So if you have a source that is located here, then the oscillation probability is something like, I don't know, maybe a per mil or going up to 1% or so. And you see that you have this quite complex structure here because it depends on the magnetic field and the projection of the magnetic field along the line of sight. Okay, so I think I have maybe 5 minutes left. So let's just briefly touch on the searches with AGN. Okay, so the idea is you have your AGN source. Some of the gamma rays can convert into X-like particles. They can actually circumvent absorption here. This is one feature we can look for, as I said earlier, or you have an oscillation into X-like particles and then we cannot observe them. This would be these oscillations that we can see. Okay, so let's talk about circumventing absorption. So this I showed you yesterday, right? We have an emitted spectrum, and if you only have absorption, no X-like particles present, this is what we would observe. So if we have axion-like particles, then a tiny fraction of the gamma rays will oscillate into axions. They will not be attenuated. And then from this tiny fraction, another tiny fraction, because you need two oscillations at least, will be reconverted back. So at some point, you will get a boost in your gamma ray flux. Yeah, if you compare this, strong absorption, and here you have some of the reconverted photons here. So if you actually measure this, and then you use your favorite EBL model to correct the spectrum, right? So you assume a model that gives you this, and you multiply it with this, then what you will see is that the intrinsic Blazer spectrum will look something like that. Yeah, and this upturn occurs where the optical depth is larger than 1. So this is not really something that you expect in standard AGN emission scenarios. So have you seen this effect? Maybe. So there has been a debate for maybe 10 years or so in the literature, and it depends very much on the EBL model used and your analysis. It depends how much you trust the high energy data points in your gamma ray spectra. And here are just 2 papers that I wrote together with a friend of mine, this latest one where we try to review critically the state of this. And well, if you ask me, I don't really think that there's much evidence of it at the moment. Okay, so there's just one more point I would like to cover now before we stop, since this will be important for the hands-on session later. And this is photon axion searches from this particular source, which is a wonderful composite image of NGC 1275. It's a Hubble image. In the center you have X-ray emission, and it's a radio galaxy. So it's not a blazar. The jet is not pointed towards us. We have a large misalignment between the line of sight and the blazar, and it's called NGC 1275, and it's a very bright source in the Fermi energy range. And it nicely sits at the center of the Perseus cluster, where we have an idea about the magnetic fields in the center. They should be as high as 25 microgauss, so really large. So what does that mean? So now we have our Fermi satellite here. We observe some gamma rays, and we observe some oscillations here. So let's consider magnetic fields. Let's consider the magnetic field of the Perseus cluster and the Milky Way. And let's just use a conservative estimate of the central magnetic field of 10 microgauss. So the magnetic field then looks something like this. Okay, so it's very turbulent. Yeah, it goes up and down here. This is the electron density that we have from X-ray observations. So this is the magnetic field inside the cluster. And this is the magnetic field and its 2 projections of the Milky Way. Okay, so from this, you can then calculate photon oscillation probability, and this is what you find. So as a function of energy, for this mass and this coupling, this is what you would expect, these turbulent oscillations here. And you see there are many lines here. I hope the projector is good enough, because the magnetic field is turbulent, so we don't know exactly which orientations it will have. So we need to test many of those, which will make the analysis a little bit more complicated. So we have looked for these oscillations using Fermi-Lat data. So this paper is already, oh my God, it's already 6-7 years old. So back then we used 6 years of Lat data of the source and then did a log likelihood ratio test, which we'll touch upon in the hands-on session. And we actually calibrated this test using Monte Carlo simulations, also something we'll touch upon. So here's the observed spectrum. So we could use this very, very fine binning. And this light red line is the fit without axions, and this dark red line is the fit with axions for this mass and coupling and one particular realization of the magnetic field. And then you could compare, okay, is this fit actually preferred over this fit? As it turns out, it's not. And we can actually then derive constraints. So this is coupling versus mass, and we could rule out everything in this black region here. So I won't say more about this this plot here, only that from simulations, we get these limits. So actually the observed limits and the simulated limits, they agree quite nicely with each other. Okay. You can play the same game with CTA, and this we will try actually later. Yes, I should stop, right?
About 5 more minutes at most.
Yeah. No, I'm almost done. I'm almost done. Thank you. So we can observe the source also with future CTA observations, and this is what we simulated here, 10-hour observation of a flare, because we've seen flares from this source. And we did a full likelihood analysis of this, and what we found, and we will see this in our hands-on session, you will actually do this yourself later today. We could see that we can probe sort of this patch of the parameter space, being quite conservative because we also incorporated systematic uncertainties here. Okay, and with this, I'm done. So conclusion from photon-ALP mixing, astrophysical magnetic fields are ubiquitous in the universe. So lots of places where we could have photon-ALP oscillations. We could have photon-ALP mixing in different sources, and gamma ray and also X-ray observations provide some of the strongest constraints that we have on the photon-ALP coupling, as you can see here again in this plot. So these are essentially all this M87, also this source here and Hydra A. These are all limits that we get from X-rays looking for these oscillations. And then here we have the Fermi limits I showed you before. Here are limits from quasars. Here are limits for magnetic white dwarfs, where they look for polarization. So these are really some of the strongest limits that we have today in this low mass range. Okay, thank you for your patience and suffering through some mixing equations. And I'm happy to take any questions. And if you don't like to ask questions, you can also use Menti and just type it in here if you're not on Zoom. Okay. And it would be great if you could use the microphone as Farnaldo just did, then I can hear you very well and hear your questions.
All right, I thank the speaker. Questions?
Thank you for the lecture. First, I would like to know, for example, is it possible to try to know the magnetic field of a target, for example, astrophysical object, without considering ALPs or something like this? I mean, if I could know, okay, let me first think my question exactly how I want to say, then I will ask.
Okay.
But I have another.
Yes.
But I have another. I will try this. My question is, for example, if I have a dwarf galaxy, for example, and we have a gamma ray burst comes from that. So in this case, we could think it may be a WIMP annihilating and generating this signal. Or we could think, for example, something related to an action like a light particle, if we have a sample of these bursts. Of course, it's not something easy, but suppose it. So how could we, for example, differentiate or something like this in this case? For I mean, what candidate would be more we could have in this case?
Yeah, okay. So first off, for this photon-ALP mixing that I talked about here, you need a gamma ray source. And from the gamma rays, or a photon source, and from the photons, you get through these oscillations, you get the axion-like particles. So all this actually does not assume that axion-like particles are the dark matter, right? You actually they could be a sub-fraction of the dark matter density, and you could still get these effects, okay? So if you're thinking, for example, of a dwarf galaxy where we believe there's lots of dark matter, then you might see this in annihilation signals from WIMPs. If the dark matter was purely made up out of axion-like particles, then okay, you need some mechanism to convert them into photons. So for example, if you had neutron stars in these galaxies, then in the magnetospheres of neutron stars, you could convert some of the dark matter axions to photons, but these would then have radio frequencies. So people are actually looking for such signals from neutron stars in our own galaxy.
Yeah,
So
I
that
see.
dark matter, yeah. So this is definitely, there's a big difference there. So if you have your dark matter axions converging to photons in whatever magnetic field, because it's cold dark matter, they're very slow, yeah, you will get radio frequency signals.
Nice.
And you only get the gamma ray signals if you sort of start with gamma rays. You first need your gamma rays plus magnetic fields or some conversion mechanism. You could also have conversion in supernovae. I didn't cover this here. But then, yeah, you not necessarily need the axion-like particles to be dark matter.
Okay, thank you.
Hi, thank you for the presentation. It was very nice. I have a very technical question. When you showed the Lagrangian, there are connected term called Euler-Heisenberg Lagrangian, right? I am very yes.
Where is it? Sorry, that was too far.
It was in
the
beginning, I think.
In the beginning here.
Yes.
This one.
I don't really understand because I thought that the connected term was just Maxwell field. So where does it come from? It's standard model physics. Is some tree level or loop level? What is the origin of that?
Yeah, so it is only standard model physics, and you're actually giving the answer yourself. So this is if you would write out explicitly the first loop order corrections to the photopropagator. You want to include this explicitly in your mixing equation or in the equations, then this is the term. So these are Feynman diagrams that look like this. They give rise to this Euler-Heisenberg Lagrange.
Just the propagation, okay.
Yeah, exactly.
Right, thank you.
My question that I forgot that time, it was like, for example, if I could trace back the magnetic field of a source instead of, okay, we have the mixing between the photons and the LPs, and we can see that from a magnetic field. But instead, with measure the magnetic field of a source, we see it changing over time. We could also constraint our ALP, for example, model using this changing in magnetic fields?
Okay, so usually these magnetic fields, for example, if you think of galaxy clusters, so I mean the length scales that are involved are so large that we don't think that over the term or over the time span of an observation that these magnetic fields will change. So usually what we do is the other way around, right? We get some information about the magnetic fields from other wavelengths, from radio observations, first and foremost, in order to get a prediction how much photon axion-like particle oscillations we should see. So it's usually the other way around. And then also remember, so the photon axion-like particle oscillations, they will not affect the magnetic field. This is somewhat static outside, right? It's an external magnetic field. So the oscillations won't change the magnetic field in time.
Hi, Manuel. Thank you for the presentation. So when you were talking about the energy oscillations in that graph, that, by the way, you use it in the quiz. You mentioned that this energy oscillation could be imprinted in the AGN signatures. How exactly? Yes. How exactly this could be imprinted in AGN? What do you expect to see?
Yeah. So let me go to the last point. I had to be a little bit fast here. So when we talk about NGC 1275, for example, right? So okay, in principle, the idea is that you don't start with axions, but you start with gamma rays, and then you calculate the probability that you end up with rays. Sometimes we call this the photon survival probability. I should have been clear on that. So this is essentially here. Okay. So you start with a photon, then you want to end up with a photon. Okay. And this photon survival probability for the particular model of the magnetic field that we chose for the pasta and the Milky Way, which is shown here, is. So let's zoom here maybe a little bit. Okay. So action of energy. This is the photon survival probability, and you see the thick line. And then essentially what happens is that you multiply this P gamma gamma, you multiply that with your intrinsic spectrum. And this is observed. Okay. So what you should observe then is essentially, where did the plot go now? Did I delete it? Okay. Sorry. Oh, did not. Where did it go? Okay. Never mind. Sorry. Okay, let's go back. So essentially what you would see, so this is your intrinsic, or this is the spectrum without axions, this green dashed line. And then what you would observe then is this orange line, if you had axion-like particles. And in this simulation here, we did not include the axion-like particle effect. So this is why the residuals that you see down here for the orange line are much bigger, right? And if they're big enough, then you can say, okay, we can rule out this particular model. Yeah, so this is what you would expect to see if you had axion-like particles or some magnetic field realization and with these mass and coupling values.
Okay, thank you.
You're welcome.
Thank you for your presentation. I would like to ask you about, can you go to, that plot, the previous one.
The previous one, yes, this one.
No. I mean this exclusion parameter space.
This one.
Yes. So my question is about axion-like particles, but they can be dark matter, but for instance, their relic abundance is too small today. What are the prospects to find these particles but behaving like relativistic particles, for instance?
Okay, so if, for this line, here particles make up all of the dark matter.
Mm-hmm.
If they're only a subfraction, then you would move up here, okay? But as I said before, so for all of these searches, you actually don't require axion-like particles to be
sorry, can I
dark matter.
interrupt you? Because I thought that above that Dutch line, those candidates were already excluded because they maybe gave you, they give you a time life below the acceptable to be a cosmologically stable particle, or not?
No. Okay, sorry. No, let's go back. And let's go back to the overview plot, okay? Here, okay? So essentially, let's move this out of the way. Okay, so what you, maybe annotate this. So all these blue ones here, these blue shaded regions, they come from the fact that axions would decay, okay? So if you have large masses, so the large masses, large couplings, then the decay time becomes too short. So this is essentially what gives you these constraints. This is all, these blue constraints are from the lifetime, okay? And all here, everything that's here, let's say, and this part, this is okay with the lifetime.
Okay.
Yeah. But then you have a constraint from the initial misalignment mechanism, and that tells you, okay, that axion dark matter needs to be below here as well.
All right.
So there's maybe some intercept here. So and everything that's in here, there you could have axions making up the full periodic abundance of dark matter and have a lifetime that is long enough so that they don't decay.
Okay. But what about the, for instance, relativistic axions? What are the prospects to find out those experimentally, those kind of axions? Is that possible?
Okay, so so the actions that we are actually looking for, produced from gamma rays through oscillations, they are actually highly relativistic. Because, right, they have gamma ray energies and masses that are very, very small. So they are ultra relativistic.
All right. Mm-hmm.
Yeah, but these are not dark matter axions, right? They are produced along the line of sight.
Okay. Thank you.
Yeah? Yeah, okay.
Okay,
There was also
guys,
one question.
One
Sorry.
last question?
There was also one here. Can you explain again the last plot on slide 80?
Okay.
Slide 80. This one. Okay. This one here. Yeah, okay. So the idea here is, right, so, sorry. So you get to this, right? You have your intrinsic spectrum. Remember yesterday's lecture? This is F. And this here is, okay, I need to draw with my mouse. This is F e to the minus tau. And tau is given from your EBL model, right? No axions here. So if you have axions, then you have this additional boost here, right? And in order to get here, what you multiply is your observed spectrum. Let's call this F prime is the observed spectrum. And to get to this spectrum, you would now multiply with, oh, I can't draw, sorry. My fingers are too clumsy. You would multiply with e to the tau to get to the intrinsic spectrum. And then you would get, because e to the minus tau, so tau is large here, so you would multiply this with a large number, bringing this up extremely high. And this is what you then would get. Which is, of course, physical, because you used essentially the wrong model to correct your observed spectrum, because you didn't account for axionic positives. Hope that makes sense.
Okay. So, nothing else? So let's thank the speaker again.
Thank you.